Okay, so then I am very excited to introduce our closing keynote speaker. Dr. Bert de Jong from Lawrence Berkeley National Laboratory is the director of the Quantum Systems Accelerator. This is another one of the 5 Department of Energy National Quantum Information Science Research Center, and it will be next year's host for the US QIS Summer School. Bert is a distinguished scientist at Lawrence Berkeley National Laboratory, as well as well known for his research in applied computation for scientific discovery, and also a personal collaborator who I enjoy working with quite a bit. So Bert, I'll hand it off to you.
Cool. Thank you, Travis. Yes, Travis and I have been collaborating for a long, long time already, and hopefully we can do that for many, many more years. Well, good morning, everybody. Last day. I still see a lot of enthusiasm. People are not falling asleep yet. People are wanting more. I'm not seeing a lot of excitement, actually, but that's okay. I'll try and give you a little bit more excitement. So what I'm going to try and talk about is a little bit about quantum that is happening at Berkeley Lab. As you can see, I lead the Quantum System Accelerator. I'm also leading some other programs within Berkeley Lab when it comes to quantum. So I'm going to give you more of a portfolio of what we do at Berkeley Lab, and also talk a little bit about things that you could potentially have a role in. Okay. So, by the way, there is another summer school going on right now. Actually, that just got done this week too. It's called QCamp. So the Quantum System Accelerator actually hosts a program called QCamp, which is for high school students. So we had, I think, about 200 high school students this year. They're in New Mexico, they're in California, they are in Colorado, Chicago area, and even we have some teachers in Pennsylvania. Yeah. So this is really spearheaded by Megan and Faith. They've been driving this pretty hefty. And this is also this is actually a 4-week program. That's not even a 2-week program. So it gives you a sense how crazy things can be. But we have a lot of excited students there that eventually will go to college where you guys are, and then hopefully show up at this summer school in a couple of years. I know, Dr. Travis, one of the things that gather you guys are interested in is try to understand what you could do to find other opportunities in Berkeley Lab. Well, there's lots of opportunities within the Department of Energy to actually have participate in programs and spend sometimes a long time at the National Lab. The only problem is most of these programs require a US citizenship. So I know there's lots of you that may not have that. Now, I want to give you a very different view of that. If you feel like you want to find a way in a National Lab, go to a conference, find a National Lab person, talk to them. Don't cold email a person. Build up a rapport, build a conversation, go to a conference, express your interest, and then you can follow up and have a conversation with them. It works with me. If you find me at APS, because a lot of you will be at APS, I hope, find me there, have a conversation. Talk about your interests, and I'll see if I can find a way to actually fund that through some of the programs that we have beyond these. So there is a lot more opportunities. Right now, I actually have 7 students that are running around at Berkeley Lab doing research. So, and I can tell you, none of them are US citizens. So let's get back to the main topic, that is quantum computing. And that's my interest. And we know, everybody has seen this slide probably in some form in the last 2 weeks, is there is big promise, right? Algorithmic speedups over classical computing, quantum simulation, which is really what drives me in a lot of ways. I'm a computational chemist by training, so I'm not a quantum physicist. I'm a computational chemist by training. I want to solve chemical problems, and I use classical computers and quantum computers to actually solve these kinds of problems. And then there is a real the opportunity for optimization in these kind of algorithms. But of course, over the last 2 weeks, you must have heard a lot about the challenges of actually achieving useful quantum computers. I think we get to a point where we have almost enough qubits that we can do something interesting with it. But the problem continues to be coherence. The available compute time is still very short. Hundreds, maybe thousands of ops now. And of course, this is all driven by noise. So we have been working a lot to do error correction, error mitigation, and other approaches to extend the effective coherence time. But there is still a lot of work that has to be done. And interestingly, then on the other side of the coin, you can have hardware, but also on the algorithmic software and compiler tools, there is a lot of opportunities to develop quantum computing further. It really is a path that I think always looks at from this point of view, is that if you want to move forward to quantum, there is work that has to be done on the hardware side, and there is work that has to be done on the algorithm and software side. And I can speak from especially the software side, and I'll talk a little bit about the hardware later, but the key part is that we are still trying to figure out how we actually do efficient quantum computing. We take algorithms that we developed or thought of in the classical world and try to translate them into quantum computers. Maybe we have to really revisit that and start to think from scratch. What would it take to take full advantage of the quantum resources to get the best, most efficient algorithm to get our computation done? So let me switch a little bit to Berkeley Lab. So Berkeley Lab really has a full stack effort for quantum information sciences. So we go all the way from the low-level software algorithms to controls, building control hardware, building control infrastructures, do prototyping for processors, controls, and sensors. And we actually are the home of 2 quantum testbeds. If you look at the research that is done at Berkeley Lab, as you can see, the top 2 layers, those are the programs that I currently manage, the Quantum System Accelerator. These are large centers, and probably Travis talked about that already. These are centers that are 300, 350 people large. The other programs are a little smaller. They're about 50, 60, but they're working on quantum algorithm software. And then we have the test beds. But we actually have a lot of applied research too. So we have high-energy physics teams working on quantum information sciences. We have physics and chemistry and materials research teams working on quantum information sciences through understanding the strong correlation materials, or actually developing new materials that could be used in future quantum computers. We also have a lot of, like any national lab, a lot of user facilities or capabilities. So we have the advanced light source. So if you get a chance to come and visit Berkeley, the advanced light source is always an interesting beast to visit, especially since of its long history. We have the molecular foundry that has a lot of tools to do materials research, and they have gotten a lot of new quantum focused tools into their suite. And then NERSC has its own programs now for quantum information sciences. And as I mentioned, the test beds are on the bottom, and I'll go through those in a little bit detail. The Advanced Quantum Test Bed is a full stack piece of hardware, superconducting qubits. And QuantNet is a pretty new program to actually try and move information from one side to the other between 2 different quantum computers. Molecular Foundry is one of our user facilities, as I mentioned. We do a lot of work in materials research. Our newest tool is what is in the upper left corner there, which is called the cluster tool. It's a capability that allows us to build extremely accurate chips, very accurate surfaces, and control every aspect of building a superconducting qubit, or actually a chip that could be used in other technologies as well. Okay, so that was a little bit about Berkeley and all the things that are going on. I'll talk a little bit about Quantum Systems Accelerator, since that's our flagship program. So we're really focused on catalyzing the national leadership in quantum information sciences through the co-design, and that's the key part that we're focused on. Co-design of quantum devices, algorithms, and engineering solutions to deliver quantum advantage for DOE specific applications. So we're not after breaking crypto, we're not breaking keys, we're not trying to make money. We want to solve DOE science problems. So where do we see ourselves? NISC is kind of the hardware that is out there right now. Fully fault tolerance is not the target yet. We're trying to move towards that. And so the quantum system accelerator really fits in between. And we're really, after 4 years, we really are starting to hit the top of that peak, and we're moving closer and closer to actually building quantum advantage. So the quantum system accelerator chose a strategy around 4 major challenges. Quantum systems are imperfect, so how can we reduce the performance limiting errors and coherence issues? The controls that have been there are not extensible. And it is independent of the technology, and I'll get to that in a little bit. Scaling quantum controls is hard. We also need to understand what we can actually do with a quantum computer. Sure, we've seen the applications in chemistry and optimization, but have we really truly explored how we can take full advantage of quantum computers? And once we get there, how do we know that we actually get a quantum advantage? How do we actually know that we get something that we can do? So our approach has been to develop advanced prototypes, and of all the centers, we do something that is pretty unique. We work in atomic systems, ionic systems, and superconducting qubits. So the atomic and ionic is something that is unique to our center. We work a lot on FPGA and controls. We have been doing a lot of near-term applications, and then developing benchmarking protocols for quantum advantage. And to give you a little bit of a sense, as you can see, we moved through this. Here are some of the highlights of activities that we have done. We've built a 256 neutral atom quantum simulator, which is an analog system, not a digital, an analog system. We built a 30 qubit trapped ion system. Actually, that is, so we demonstrated that, but we also designed a 200 ion trap now, which is called Enchilada, coming out of Sandia, our partner. This one has now moved to Duke, and they're starting to slowly load ions. Now, a 200 ion trap, you're like, okay, there's lots of people that have ion traps, companies that have ion traps. Actually, doing 200 ions in a trap is hard, controlling them. So it's not even about doing 200 ions, but it's actually trying to figure out how you control 200 ions in a trap like that. We do a lot of work on the superconducting qubits. We have a 16 qubit right now, but by the end of next year, we should have a 72 qubit with a lot less crosstalk. We've been developing 3D integration for a lot of our quantum platforms. The atoms and trapped ions really could use integrated 3D integration and controls so that they can actually get the highest performance and not lose a lot of information as noise. We've done a lot of work on making applications work, trying to figure out how you actually do multi-qubit gates on trapped ions or even on neutral atoms is not trivial. And then we've done a lot of work on actually starting to demonstrate protocols that could tell us if something is a quantum system and if we can actually get advantage out of it. So I'll give you a couple of examples of firsts that really have come out of this center. So the Harvard team was the first to develop something that allows them to reconfigure neutral atoms. So what's the nice part of this? You can actually put atoms away and you can put atoms together, interact them so that you can do quantum operations and then move them away from each other so they don't interfere with each other. They figured out how to do very efficient loading of these systems because if you just have a grid that uses just little potential wells effectively to store your ions, it's not trivial to really uniformly load them. So they figured out how to do this in a more efficient way. On top of that, we've been able to develop the highest fidelity 2-qubit gates. So 99.5 on a neutral atom system is extremely high. And the interesting aspect of this is that the combination of these high fidelity gates and being able to do reconfigurable neutral atoms allowed the team to take on a DARPA project to actually show a first demonstration of some level of fault tolerance. Now, this is all advances of technologies. We've done this also with clock qubits, so not just the standard neutral atoms that are being used, but different types of neutral atoms. And they have been able to use these to actually do some science. So we've been able to look at quantum mechanism in these Rydberg arrays. We can do a lot of lattice spin models. And the interesting part is we're now moving from atoms also into molecules. Why? Because with molecules, you have more degrees of freedom. And that gives you potentially more than a 2-level system, or a 3-level or a 5-level. You have a lot more levels of that you can take advantage of. We're also working, the Colorado team is working very hard to actually do something that couples these neutral atoms with cavities to actually do more types of interactions. So this is progress that has happened. There is continuous progress that has to happen to really make these platforms useful. There needs to be work done to effectively reduce the temperature a little bit. Sure, we can do neutral atoms at room temperature, which is a unique feature of these platforms, but that still induces noise. Can we actually do things to cool these kinds of systems down a little bit more? So trying new atoms and molecules is a major effort. New gates. And the key part is that a lot of these technologies are driven by not just single 2 atoms or 2 qubits interacting, but 5 to 10 qubits interacting at the same time. So one of the side benefits that came out of this effort to really better control atoms is actually that they got better at metrology, i.e. measuring qubits. And so we now have a situation where we can actually get 10 to the minus 21 accuracy on an atomic clock. This is a side effect, but it allows you to use atomic clocks for better measurements in the future. Now, this is experimental, but still, we move this field forward. The other thing that they have been able to do, and that shows you another demonstration of there is actually measure a gravitational redshift in a small sample of atoms. So now, again, you can measure very accurately. And again, this is an interesting thing to think about. So I was talking about quantum computing. This has nothing to do with quantum computing. This is about measurement and about fundamental physics problems. This is actually an interesting thing you have to realize. We can actually use these quantum systems to tackle and probe other physics systems. So we were able to do this at the length scale of a quantum wave function effectively. Okay, so that was neutral atoms. There's a lot of excitement that has come out of our center around that. The ions is also a very interestingly challenging problem. As I mentioned, we now have a trap that can store potentially up to 200 ions. We haven't done that yet because you have a trap, but now you need to have the controls to actually store 200 ions, which is a very big problem. So they're developing new integrated light collection optics to do better measurement, but also for the better control. There's a lot of effort going into doing dual species so that they can do sympathetic cooling. If you take an ion that is not interacting, but interacts with your target ion and cools it down, that's a benefit, right? This is a way to cool the system, especially if you have to do operations, because every operation you do, you put energy into the system, and you don't want that. But using these systems, using these technologies, they were able to do some interesting things. So this ended up being a very interesting work where they actually were able to do something that computer theorists have envisioned when it comes to certification of a quantum computation. They devised an algorithm, an approach to do this, but it required some features that didn't exist at that point in time. So they actually had to develop a mid-circuit measurement approach through ion shuttling, and they had to develop a novel n-qubit way to do a lot of operations between multiple ions. These technologies were needed to be able to solve a science problem like this. And this is one of those examples of true co-design. The theory says one thing, how to get there requires all of this. There's a lot more work that has to be done. Again, we need to do a lot of more work to do optical delivery and collection. We need to improve our detectors, and we need to develop some novel optical cavities that allow us, again, have more degrees of freedom when we solve our problems. When it comes to superconducting qubits, so all the centers have in some way are working on superconducting qubits. We've taken a slightly different tact. We've been focused on building 3D integrated chip technology, really figure out how we can use multiple layers of a chip stack to move information between qubits. Instead of putting it all in one layer, it doesn't work. The nice part is that we've been able to show a reduction in crosstalk because of it by an order of 50. That allows you to go a lot further with the number of operations that you can do. You can see that actually here, this is, what is it, 18 qubits. As you can see, there is very little crosstalk because there is not a lot of color that is on the off diagonals. So that's a good thing. But really understanding how it works, how you can build these chips in a efficient way, in a sustained way, is a research topic on its own. We're also exploring a lot of different types of qubits. Everybody is familiar with the standard superconducting qubits that are being used. We've been focusing on Floquet, Kerr, and grid state qubits, and actually building these kinds of chips. So these are not large systems. These are single qubits or maybe a couple of qubits that we're trying to understand how we can take advantage of those kind of technologies. How can we do they reduce noise? How can we operate on them? They are not always trivial to operate on. So we then took some of these technologies and did some, this is one paper, there is a couple of papers that have been able to now take this to do standard material physics problems. This one is a demonstration of an entanglement of 16 qubits and doing the metrology in an accurate way, very close to what you can do on a simulator. So that means we can actually do these kind of things very accurately. And then there's some other experiments that have been done. The superconducting qubits have a lot of interesting challenges. So we're demonstrating these grid qubits, but how do you package this? So this 3D flip chip technology becomes then even a broader question of how do you do advanced packaging? How do you then do the wires? Because a superconducting qubit, one of the big challenges is the wires. And by the way, not just the superconducting qubits, the neutral atoms, the trapped ions. At a certain point, either you have too many lasers or you have too many wires that have to go in. And so there is a lot of work that is being done here that has drawn a lot of attention from industry. And then there's a lot of work that we've been doing on developing a control system. You guys, some of you guys worked on KIC here for the last 2 weeks. There is an alternative to that. And this is something that has been developed at Berkeley lab called QBIC. QBIC is the similar FPGA implementation, although it has a lot broader capability. And it has been taken up by a lot of different institutions now. We have a very cost-efficient solution. And this is the real reason why QBIC was developed. It costs you 10,000 or so per channel or 30,000 a channel on a superconducting qubit for a commercial solution. we can do it for less than 1,000. And I think there is more room at the bottom. Now, that's hardware technologies. That really has been the focus for a lot of things here in the first 4 years of that center. There's also a lot of efforts in theory simulation because there is a lot of co-design again that is needed. People are trying to figure out if we can build new types of superconducting qubits. So these are extended Josephson junctions that could potentially hold multiple qubits in one cavity, and you could potentially do multi-qubit interactions in a lot more efficient way. We've been doing a lot of work on benchmarking. So randomized mirror circuits has come partly out of my AQC center and also now at the Quantum System Accelerator. So we have a very efficient, scalable benchmarking approach that allows us to actually quantify how good a circuit is, how close we are to the right answer. We've been starting to use a lot of more machine learning in these days, and that is to really do something like continuous quantum error suppression. So not at the end, no, in real time. So we probe a little bit of the information over time and learn whatever we can from that little bit of information that we siphon off of the quantum state and use that to do some level of quantum error suppression, not error correction, suppression. We know what the error is and we try to minimize that effect. So last slide on the Quantum System Accelerator. So this is what it looks like. We are about 300 people. These are all the institutions that are involved. So it's 3 national labs, 2 DOE, 1 DOD lab, and then 12 universities. This number is low. We're getting closer to 400 papers by now. And I mentioned this, the high school students. We've been growing this. And the interesting part is there's so much excitement about, you guys are excited about being able to do this for 2 weeks. Look at the high school students. It's insane. We had like 500 applications and we can't host them all. So there is a lot of opportunities and states are seeing this as an important thing right now. So actually as a grad student, there is an opportunity to be involved in these kinds of things too. I actually have a lot of postdocs and grad students that have been helping with QCamp, help teach the next generation. And you should start thinking about that. That's going to be part of your legacy as a researcher. It will be that you also help develop the next generation. So I already talked through these, so I don't want to go through those, but this is what the Quantum Systems Accelerator is about. I want to briefly talk a little bit about the Advanced Quantum Testbed. This is something that might be of interest on those that are really focused both either on algorithms or on hardware. So they're really focused as a advanced superconducting platform for full stack quantum computation. So they have an end-to-end system, similar to an IBM system, much smaller scale. But the key part of it is it's a white box. So if you go to IBM, you only get access to what they give you. So the interesting part of the Advanced Quantum Testbed, or AQT, as it is lovingly called, is that it is full stack and access to everything. You want to do new controls? You have a new idea about controls? Okay, let's go work on the software stack or actually at the hardware controls. If you have a new FPGA idea, you can work with them to actually implement them. They do a lot of work with the understanding how they can get the most out of the cryogenic platforms that they have. And they are trying a lot of different things when it comes to superconducting qubits. And again, all of this is accessible. This is a user facility. So you can write a short proposal and actually get access to this or come and visit us for a while and do research. And that makes it unique. It's a unique platform. It leads to deep collaborative user engagement. This is not like here, go send a job to IBM through Qiskit. No, this is really trying to understand how you can get the most out of a quantum system. They broadly explore technologies and are eager to have people come and say, I have a new idea that can make things a lot better. So to give you a sense, so these are some of the qubit technologies that they have been developing. Simple qubits, 8-qubit systems. They have done some work on parametric, but I think one of the ones that I find very exciting is what they call SpiderNet, which is designed to actually do all-to-all. So all-to-all in superconducting qubit, that's hard. Again, if you do simple qubits, it's high coherence, it's easy to do hardware-wise. If you want to do something that allows you to play around with gates and the complexity of gates, they become a lot more configurable, but it's a lot harder to get them accurate. So the challenge is, where do you want to be in this space, and what can we do to get the most out of a quantum processor? And one slide about the QuantNet. QuantNet just started last year. So their focus is really building a quantum network testbed using some entanglement technologies to really build a proof of concept to connect two different types of quantum computers. So they want to do a spin qubit and a superconducting qubit and connect them through a effectively classical network. It's not that easy because all these networks have a lot of noise. And so there's a lot of work that has to be done to actually build these kind of technologies. As I said, this is a relatively new program, but they're already making some significant progress. Okay, switching to a little bit of the other programs that I have. And so one of them is AQC. This is in its last year, but still, it has been one of those programs that has been run for 5 years and has been critically important to move quantum information sciences forward. We were really focused on developing an open source programming and simulation environment for the large number of technologies that are out there. So there's a lot of work that was done on languages. I would say our biggest success story has been around the cross-platform compiler for circuit synthesis and optimization. And I'll show you an example of that. We really focused on something that is hardware agnostic. So building compilers that are not just for a superconducting qubit, for example. We developed some tools to do verification, as well as some tools to develop debugging approaches. Again, the mirror circuits that I mentioned earlier partly come out of this work of trying to figure out how you can do verification and debugging. Because if you really want to do quantum computing, you need the whole stack. You cannot just run and hope. So one of the things that we did, we actually developed what's a very flexible program environment. So a lot of this work actually on the programming side was done here at Oak Ridge. Now that actually then got adopted by NVIDIA. So that means I would say is a success story. We developed something that people want, right? And that's the key part. But the key part for this was that it was platform and programming language independent too, because I think most of you are really into Python programming because that's what mostly has been taught, but there's a lot of opportunities to do it with different languages too. As I mentioned, compilers, I think, has been our biggest success story. There is commercial compilers out there. This is the ticket that you may have worked with in your efforts to run simulations on quantum computers. Biscuit is what comes out of Berkeley lab. I would claim that Biscuit is one of the most efficient and most scalable compilers out there. We can handle 1,000 qubits without a problem. But we also are able to get probably the shortest circuits you might ever need on a quantum computer. So there's a lot of different tools that are in here, but they are by now one of the most efficient compilers out there, and they are being adopted by companies like Quantinuum is actually using Biscuit now. IBM has a version in their software stack, and other companies are also adopting it on top of a lot of faculty are seeing this as an open source compiler platform that they can expand. So we have a lot of contributions that come into this platform. But I can want to put one thing forward. Compilation is going to be fundamentally an NP hard problem. So effectively, you need a quantum computer to compile a quantum computer, right? So large qubit counts, that means you have to use HPC. So the systems like Oak Ridge or NERSC, which is at Berkeley Lab, are critical to actually do these kind of things. We have some ways around it. We do not do the full NP hard problem. And most of the science problems that you want to translate onto a quantum computer have some level of sparsity. They are not strongly correlated all the time. And it allows us to get away with a lot of things to actually do the compiling a lot more efficiently. So I'll give you a couple of slides on the fun part, how I started. So this is now 4 years old, but I think it's still a very interesting thing. So we initially, we stood at the root of the quantum subspace expansion. So my postdoc, Jared McLean, did a lot of work doing the quantum subspace expansion that allowed us to effectively do some correction on our estimated ground state and get a better result. We've taken that even further and now demonstrated just simply that you can actually do excited states with this. So for those that don't know what the quantum subspace expansion is, we effectively find our state. We do a couple of additional measurements. Actually, those measurements do already exist that get us out of the ground state into more of a larger Hamiltonian space, a larger matrix space. We effectively generate a general eigensolver problem, diagonalize it, and then we can actually get not just the ground state, but also excited states. What turned out to be the interesting challenge is that this might be an interesting equation. So these are matrices, keep that in mind. But there is also a metric, which is the overlap. Now, if you do noisy measurements, this metric can have very weird values in there because of the noise. So we actually had to do a lot of work, and that's why we see a person like Roel van Beumen, who is an applied mathematician, involved in this co-design effort to really work to develop this in a regularized version so that we can actually get reliable results out of one of these solvers. We built on that in more recently. Katie Klimko used to be a postdoc in my group, is now a staff member at NERSC. So again, postdocs, become a postdoc at the lab, you have an opportunity to stay there long term. What's interesting, what we did here is that we can actually take the quantum subspace expansion and turn it on its head and say, let's do a real-time evolution of the Hamiltonian, extract the states, and use that as a basis, effectively a non-orthogonal basis, to solve these kinds of problems. Well, it turns out that you can take it even further. And if you start to think about it truly, and this is the key part that Katie and Norm came up with, is that if you write this generalized eigenvalue problem into a unitary form, this then becomes kind of an autocorrelation function. But the key part is that the overlap matrix gets what's called a tuplet structure, which means the values on the next column are shifted by 1, which means you only have to do n measurements instead of n squared, which of course reduces your noise dramatically. It also allows you to really extract multiple excited states for a matrix. And that's the real interesting part, because now you have to try to figure out how big a steps you have to do in the real-time evolution to kind of capture the physics of the different steps. So we had a very smart grad student work on this, a mathematician, to really figure out what would be appropriate step sizes to move this forward. The other thing that we are really interested in is open quantum systems. So this is some early work. So McKenna Metcalf was a postdoc in my group. Then she became a staff member, is now at HSBC. So she leads some of the quantum efforts at a very big bank, effectively. Elizabeth Stone was a grad student, an undergrad student that visited us. So coming out of Lex Campus Group and Moham. Anyway, so we really wanted to do something that's called open quantum systems. And this is something that have gotten more and more excited about as an opportunity. Most of the systems you want to probe are open, right? We want to get the exact ground state of a system, of a chemical systems or physics system. It's not important to some extent. It's the hard problem to solve, but it's not the problem we really want to solve. Anything we do, anything we measure, anything in nature is an open quantum system. So we've been really focused a lot more lately on finding a way to use qubits to model an open quantum system. This is some early work that we did where we actually can do finite temperature simulations of a quantum system. We have a approach where we use effectively spectral combs of the kind of spectator host qubits to really get the ground state of the qubits we're interested in into the right finite temperature state. And so we were able to do this. We have been building on this in different algorithms. But what I wanted to put out there is, you know, sometimes you do this for a certain reason. We did it for a materials problem. We wanted to get material in a finite temperature state. Once we published that, staff at Berkeley lab in high energy physics said, well, we have an interesting two-level system, which is a quark gluon plasma. It's exactly what we need to do. It's an open quantum system. So we were able to take the same approaches that we developed, the same algorithms we developed, and now apply it to a very different type of problem. And I think this is the critical part you have to think about, is that a lot of work that you do might find an application in a very different field, simply because they have a similar need. So we were able to get very reasonably accurate stuff in 2021. I would say if we do this on current IBM systems, these numbers will look a lot better. We didn't even do DMD and those kind of things. The other work that we have been focused on is some work on adaptive variational quantum dynamics. So this is very similar to VQE, but now we're not just taking a pool of operators and just doing VQE. We're actually trying to figure out what the best pool of operators is. And not just for getting a ground state, actually doing this for dynamics. So can we actually get the most optimal pool of operations that have to happen, or actions that have to happen, to get a quantum simulation run in the most efficient way? So this is based on the McLachlan distance. This has some roots in Iowa. But we've been taking that with, and actually is trying to do something that is calculating a two-side Hubbard model. It's not that big, but that's not the point. We tried to do this on 4 qubits, and we were actually trying to compute a Green's function. So I would say the Green's function that we can get out of a quantum computer is reasonably accurate. We also understand the challenges, and this is where the interesting parts come in. So these red dots that you see, that's what I get out of an IBM quantum computer. So we had to do a lot of work. So we developed some new error mitigation strategies to get to what's the yellow and green. That allowed us to get to a spectral function that looks reasonable. So again, it's not just, I need to run on a quantum computer and I get a result out. There's a lot of work that you have to do after the fact. So we actually used a trick called Padé approximation, which allowed us to actually extend this time frame a lot further. There is also an approach called dynamical mode decomposition, which allows us to do the same thing. So there's a lot of mathematical concepts that are out there that we can take advantage of to get reliable results out of a quantum computer. So we've also worked on error detection. So we have not done error correction yet, because that's an even more complicated problem. But my postdoc, Miro Urbanek, who is now actually at Atom Computing, he's their lead algorithms person, actually developed something that looks like what would be a 422 error correction code, but we never do correction. right? So we store our qubits. We have 4 qubits that we store our information in, which is 2 logical qubits. And we use 2 extra qubits to do detection. So we do post-processing. We throw away the stuff that is not good on these 2 qubits. This allows us to actually get very close to a noise-free simulator result. So you can actually do some level of error detection and post-processing. Now the real challenge becomes, can you do this at a larger scale, and can you do actually error correction? So we took that a little further, and this is a slightly bigger problem. It's a time evolution of a 6 qubit magnetic system. This is not a trivial system. It required, at the longest time, about 210 CNOTs on 1 qubit. So the number of CNOTs that we had to run is a lot larger. We actually had to run 4 different levels of error mitigation and do a lot of massaging of the data to get to this red curve. The blue is what you would get out of a quantum computer right now. Now, it will be better now because this was done a couple of years ago. But at that time, we developed a new kind of error mitigation strategy that allowed us to effectively estimate how big the errors were. We effectively took a circuit and took out all rotations so we would know the answer, right? If you don't have arbitrary rotations, it's just X gates and so on. You know what the answer has to be. We can use that information to correct our circuits. So that error mitigation strategy got then picked up by another group of high-energy physics researchers. That's Martin Savage at the University of Washington, that took the exact technology estimation circuits that we developed and then ran it on 100 qubits very recently. This is last year. So they were actually able to do a Swinger model on 112 qubits. So again, there's a lot of work that has to be done at the smaller scale, and then it can be taken by others to do bigger problems. Let's see, I'm almost out of time, I would say. So I'll skip that. I wanted to say that briefly, there is not a lot of challenges when it comes to actually doing quantum computing and thinking about how to integrate it with HPC. So this is some work that we had been doing with IBM, where we actually started to look at, okay, here's a problem that we want to solve. This is a normal chemistry problem I would want to solve. How can I run it on a quantum computer without even understanding how to use a quantum computer? So we actually were able to do this. It took a lot of effort. It took more than a year of effort to even try to figure out how to integrate a computational chemistry loop into Qiskit and then run these iterations. We were able to do that. We actually able to use the quantum computer as an accelerator for the computationally expensive part of a chemistry simulation to run the problem that we wanted to run. Okay, so AQC does a lot of different things. I hope you got that message from languages to compilers and software. And I wanted to leave you with this. So exponential speed up that everybody touts of a quantum computer is not the only factor that will make quantum computing successful or quantum advantage successful. Travis will not like this, but you know, as a frontier supercomputer is 20 megawatts, right? 10 megawatts cooling, takes a lot of energy, also a lot of cost, by the way. So what if quantum computers could solve larger problems faster compared to classical computing? That's not the only reason. Quantum computers can potentially do this more energy efficient. So what if I can do this in kilowatts? If you go and do the estimate on cost of 20 megawatts versus kilowatts, it's a big, big number. Every company would die to have kilowatt supercomputers, so to speak, versus megawatts. Believe me, Google has one reason why they want to work on this kind of field. But there is a lot more that can come out of quantum computers. And so this is how I try to phrase it. The race to the moon delivered more than, oh, we landed on the moon, right? It delivered a lot of ancillary technologies. So for quantum, so for them, it was CMOS, integrated circuits, that came out of these kind of efforts to put a person on the moon. But we can already do a lot more. Quantum-inspired algorithms speed up classical. Once we start to know how a quantum computer works and we develop quantum algorithms, we realize we can do it more efficiently in classical computers. There's a lot of novel quantum hardware technologies that will find its way in classical computing because it's more energy efficient. Even on the simplest point, if we understand the materials that drive a lot of the classical computing, we can do a lot more. So in general, I think quantum physics helps us do better classical computing too. So it's a race for universal quantum computing that already shows impact beyond doing computation right now. There's always those side effects that come out of a big challenge that you have to solve. Okay, so then that's all that I have. If you want to read more about what we do, these are some links. I'm here if you want to talk to me. Believe me, my life is finding the next generation of researchers and help them succeed. So you can always reach out to me. If you have ideas, so we are going to host the next summer school. If you have ideas of things that you think would be important to think about in the next summer school, send me an email. Come talk to me, because we want to make this summer school as successful as possible every year and make it better or different or improve on the things that you guys want to see. Okay, so that's it.
Hey, thank you, Bert. Any questions from the audience? We have some time. Kim.
I was curious how, is it enchilada, the 200 trapped ion qubit thing?
Yeah.
Is that a linear chain, or are there different trapping zones, or how does
Different,
the
so
geometry?
it's different zones, so different operation zones effectively. So it looks a lot more like what Continuum is doing.
Okay.
But Continuum is making a racetrack.
Yeah.
Where they have different operation zones or interaction zones, but they have to move the ions around. This one is a lot different in the architecture and potentially has a structure that could be extendable. So I didn't show it too good, but if you show one, if you look at one and you imagine putting another one next to it, you can build this out to 2, 4, 6, 800. But the hard part is it took them 2 years to actually design the electromagnetics for this to do it right. And now you have to try and put the ions in and see if it actually works properly.
Yeah.
So
Can you still get all-to-all connectivity, and can you couple different zones in the chip?
you can, so with trapped ions or neutral atoms, right, you can always get some level of all-to-all connectivity. You just have to shuttle them.
Okay.
Right, we have to, in superconducting qubits, we have to shuttle them too. It costs us because we have to do swaps, which are expensive. Theirs is a little easier, relatively speaking. You just move the ions around. Costs time though. So their biggest problem is not as much the accuracy, but the time. So their neutral atoms and trapped ions are a lot slower in operations and moving ions around than they are in superconducting qubits. So there's trade-offs in every technology.
I had 2 questions. So the first one was, you mentioned the reconfigurable neutral atoms for quantum computing applications. Do you know what the offhand, like how many gate operations you could get out of those types of systems?
I don't know offhand,
Okay.
but they can do, they can run effectively on the neutral atom. If you do analog gates, they can run a very long time for 256 qubits. So just do the entanglement of that. That should be thousands and thousands of operations. Digital, it's a little bit different.
Yeah. And then my second question was, you mentioned you're calculating a Green's function. It was on slide 35. But I think it was the red data that was the data you had for the quantum computer. I found that interesting because the amplitude seemed to be suppressed, but the phase was the same. I was wondering if you could elaborate on what caused that specific type of error.
So that phase is not exactly the same.
Oh.
There's also a shift there too.
Oh, there's a shift there too.
Yes. So we had to correct for that.
You mentioned n-qubit native gates on trapped ion. So can you elaborate a little bit like what's that N now and how much it can be in the future? And do companies like Quantinium, do you expect them to follow in your footsteps and start making multi-qubit native gate sets?
So our hope, of course, is if the technology you develop that shows up in industry. I would be surprised if Quantinium isn't working on n-qubit gates and definitely is learning from what is happening. I actually don't know what the dimension is that they have gotten up to, but 4 or 6 qubits is not out of the order. So that to me is already, for a lot of the problems that we want to solve in physics, is something that, yeah, opens a lot of doors.
I had a question regarding the machine learning optimization for error suppression. So could you elaborate a little bit on the general structure of the machine learning models and what Berkeley is doing in the more QML area?
So QML, in the sense of using a quantum computer to do machine learning, we don't do a lot of that.
So it's just like using, I guess, classical machine learning to try and approach error suppression and QEC.
Yeah, I don't know exactly what model they ran and what they're using, but the real challenge is not the machine learning model. The real challenge is doing a very weak measurement of the information so that you don't disturb the overall state, but get enough information to get a sense of where the error is moving, how the error is evolving, and then use that to correct effectively or suppress.
Thank you.
Hello. Hey, I have 2 questions, if you'd be so kind. So the first one is, yeah, machine learning. Do you know if anybody's using that for specifically control and calibration and readout?
Oh, yes. Yeah, so I didn't go into detail, but Cubic definitely, and the AQT system, they use machine learning to accelerate the tuning of the qubits and the gates. Yeah.
What was that second? You said cubic and Yankee? I didn't think-
AQT, so
Oh, AQT.
advanced
Okay,
quantum
okay,
test
okay.
bed, sorry.
Cool.
Yeah.
And the second question, you mentioned some stuff about like RFSoC and FPGA controllers for like trapped ion systems. Can you like elaborate on some developments or, work that's going on?
So the trapped ion community is actually using something that a different type of open source platform that is developed at NIST. I forgot what the name is, but so that community is rallying around an open source quantum platform, quantum controls platform too. Superconducting qubits, we still have a lot of different opinions on that. But my hope would be that we can get to something that is even more universal for all the technologies. Now, the trick is for superconducting qubits, everything has to be fast, right? Operation has to be fast, error correction has to be fast. We're actually integrating machine learning now into the FPGAs to do control. Neutral atoms, as I said, trapped ions, they're slow. So there's no speed challenge. So it's a little different of a problem, but they need accuracy. So in the long run, I think we'll see a convergence of some technology, because my hope would be that at some point we could take neutral atom system and a superconducting qubit system and actually put them together and take the strengths of the different technologies and solve a quantum problem that goes on both of these systems. So.
Any additional questions for our speaker? Okay, with that, let's
Cool.
thank our speaker one last time. Bert, before you take off, I'd like to give you something. It was passed on to us by the SQMS Center. It's been the hardest thing for me to keep up with all week. I think everybody here knows the bell. Bert, I would like to officially hand over
Okay.
responsibility for the bell.
Now I have to figure out how to get this home.
That's right. Yeah, good luck with that at the airport.
Exactly.
All right, folks, hold on just a second. We're going to transition over into our closing ceremony. Let's just get a few things set up.